Greetings of the day. I am Dr. Ronika Parmar and I welcome you all in this lecture. Today we are going to dive into the fascinating world of semiconductors, especially focusing on intrinsic and extrinsic semiconductors. Let's explore how these materials play a crucial role in the modern technology. Today we are going to discuss about the semiconductor materials, intrinsic semiconductors, covalent bonding of the silicon atoms, charge carriers in intrinsic semiconductors, effect of temperature on conductivity of intrinsic semiconductor. We are also going to discuss about extrinsic semiconductors, N-type semiconductors and P-type semiconductors, and energy band diagram of N-type semiconductors and P-type semiconductors. So, let us start our discussion upon semiconductor materials. Semiconductors are material that have electrical conductivity between conductors, that is metal, and insulators like non-metals. They have a unique property. Their conductivity can be manipulated and controlled, making them essential for various electronic devices. See, in a semiconductor, we can control the flow of current. We can control the conduction in the case of semiconductors, while in the metals or in the conductors, we cannot control the flow of current. Therefore, semiconductor plays an important role in today's electronic world. So, semiconductors are single crystal and compound crystal structure. The example of single crystal semiconductors are germanium, silicon, whereas the example for compound crystal semiconductors are gallium arsenide, cadmium sulfide, gallium nitride, silicon carbide, gallium arsenide phosphide. So, gallium arsenide is written as GaAs, cadmium sulfide is written as CdS, gallium nitride is written as GaN, silicon carbide is written as SiC, and germanium arsenide phosphide is written as GaAsP. Gallium arsenide are used in the case of the optical devices. Compounds like gallium nitride, silicon carbide are used in the wide bandgap applications, and in the day-to-day physics or in the day-to-day electronics or in the low power electronics, we use gallium and silicon. Gallium arsenide also has various applications. So, let us discuss about intrinsic semiconductors. A perfect semiconductor crystal with no impurity or lattice defect is called an intrinsic semiconductor. The example for intrinsic semiconductors are pure silicon and pure germanium. So, silicon is represented as Si and germanium is represented as Ge. So, in such materials there are no charge carriers at 0 Kelvin, since the valence band is filled with electron and the conduction band is empty. Therefore, intrinsic semiconductors behave like an insulator at 0 Kelvin and it behaves like conductors at room temperature. That means the resistance of intrinsic semiconductor at 0 Kelvin is infinite. At higher temperatures, electron hole pairs, they are represented as EHPs. So, at higher temperature, electron hole pairs are generated at valence band electrons and are excited thermally across the band gap to the conduction band. the electron hole pairs are only charge carriers in the intrinsic material. So, we can see here temperature plays a significant role in the case of semiconductor. We have seen that at 0 Kelvin the resistance was infinite, there was no conductivity at all. But as the temperature increases, the electron moves from the valence band to conduction band and the current flows. We can see the temperature variation causes a significant flow in the current in the case of semiconductors. So, temperature is a very important quantity when we work with semiconductors. The characteristics of the semiconductor vary with temperature. Covalent bonding of the silicon atom. An intrinsic semiconductor such as pure germanium or pure silicon has 4 electrons in the outermost orbit of its atom. When the atoms bond together to form molecules of matter, each atom attempts to acquire 8 electrons in the outermost orbit. This is done by sharing 1 electron from each of the 4 neighboring atoms. This sharing of electron in semiconductor is known as covalent bonding. The figure here shows the covalent bond of silicon atom. So, here we can see the structure of silicon and we can see there are 4 electrons in the outermost orbit. All the silicon are having 4 electrons at the outermost orbit. Now, every matter try to have a stable state, and how can we achieve this stable state? By having 8 electrons in the outermost orbit. So, what this silicon will do? So, in the case of such semiconductors, as one has 4 electron in the outer orbit and the second one has 4 electron in the outermost orbit. So, they will share their electrons. So, in that case both the atoms are satisfied. When the sharing of electron occurs, such type of bonds are formed are called covalent bonds. So, in the covalent bonds sharing of electron happens and the bond is formed and the atoms goes in a stable state. While charge carriers in intrinsic semiconductor, as the figure illustrate, generally when we say room temperature it is 300 Kelvin. So, at room temperature significant thermal energy is supplied in order to cause the valence electron of semiconductor atoms to move away from its influence. So, here we can see that there is a conduction band and there is a valence band, and Eg denotes the energy gap. So, when the electron gains significant amount of energy which is present in the valence band, when it gains a significant amount of energy, it moves to the conduction band, and when the electron moves from the valence band to conduction band, the current flow because of this free electron. Always remember, the current flows because of the free carriers, free electrons or holes. Whenever we say carrier, it can be electron or holes. So, as a result, the covalent bond is broken in this case and the electron is then free to move around the crystal as soon as this phenomenon occurs. There is a valency created in the broken covalent bonds when electron breaks a covalent bond and moves away. The valency is referred as holes. Free electrons and holes are always generating free electrons and holes are always generated in pairs. Therefore, the concentration of free electrons and holes will always be equal in the case of intrinsic semiconductor. Let's understand this thing once again. So, what's happening here is the covalent bond is broken, and when the covalent bond is broken, the electron moves away. So, there is a vacant space. The vacant space generated due to the electron is called as holes, and in the case of intrinsic semiconductor or pure semiconductor, the number of holes and the number of electrons will be equal. Okay? So, if N represents concentration of free electrons and P represents concentration of holes, then as I said, number of holes will be equal to number of electrons, and this will be equal to Ni. Ni is intrinsic concentration. So, let us discuss the effect on temperature on conductivity of intrinsic semiconductor. At absolute zero condition, the semiconductor behaves like an insulator. When it is heated, its temperature increases. Due to the thermal energy, the electrons which are involved in covalent bonds break away from their atom. These electrons move from the valence band to conduction band. Such free electron can constitute a current. When free electron is generated, a hole is also generated in valence band. Such holes also help in conduction. Increasing the temperature, that is increasing the application of thermal energy, more electron hole pairs are generated. Hence, large number of free electrons are available for the conduction. The semiconductor behaves like a good conductor at high temperature. Thus, as the heat, that is temperature, increases, the conductivity of the semiconductor also increases. This indicates that the resistance of the semiconductor decreases as temperature increases. Hence, the semiconductor is said to have a negative temperature coefficient. So, what's happening here is the atom gets energy in the form of heat, and the electrons from the valence band goes to the conduction band because of the heat absorbed by the semiconductor, and when the electron moves from the valence band to conduction band, the flow of current occurs due to this free electron. Hence, as we can see that as the temperature is increasing, the conductivity of the semiconductor is also increasing. Therefore, it is said to have a negative temperature coefficient. The increase in temperature causes to increase the charge carrier concentration in semiconductor. The relation is exponential, and we can see this in this figure. The y-axis shows charge carrier concentration and the x-axis represents temperature. So, as we are increasing temperature, the charge carrier concentration is also increasing, but this fashion of increase is not linear. Why? While it is exponential in nature. So, we can see from this graph the carrier concentration increases with increase in temperature in an exponential fashion. So, why is this exponential? Why it's not linear? So let's discuss why this increase is in an exponential fashion. This is because of the relation of intrinsic concentration between the charge carrier concentration. It is represented as Ni square is equals to A naught T cube e to the power of minus Eg0 by kT. Here in this equation we can see that Eg naught or Eg0 is represented as energy gap at 0 degree Kelvin and it is in the unit of electron volts. The value K or small k is representing Boltzmann constant. Its unit is in electron volt per Kelvin and A naught represents the material constant and it is independent of temperature. So, here we can see that the carrier concentration or the intrinsic carrier concentration is proportional to the exponential function, and in the exponential function there comes the temperature. So, the charge carrier concentration increases with temperature in an exponential fashion. Now, moving forward towards extrinsic semiconductor. In order to change the properties of intrinsic semiconductor, a small amount of other material is added to it. We can alter the property of the intrinsic semiconductor. How these properties can be altered? By adding some other material to it, and we add this in a very small quantity. So, the process of adding other material to the intrinsic semiconductor is called doping, and the impurity that we add to the intrinsic semiconductor is called dopant. Okay, and the overall result of the doping is an extrinsic semiconductor. When an intrinsic semiconductor is doped with pentavalent atom, that is an atom consisting of 5 electron and 3 holes in the valence band, is called donor doping. This creates more free electron than hole. As we can see that there is 5 electron present at the outermost orbit. So, when we dope it with silicon, there will be an extra electron with every dopant, and hence the number of free electron will increase and the conductivity of this type of semiconductor will also increase. When an intrinsic semiconductor is doped with trivalent atom. What is a trivalent atom? An atom consisting of 3 electrons and 5 holes in the valence band. It is called as acceptor atom. This creates more number of holes than free electron. Such two types of extrinsic semiconductor formed due to donor doping and acceptor doping are called N-type semiconductor and P-type semiconductor respectively. So, in this case, when we make a P-type semiconductor, we add the doping in such a manner the outermost shell of the dopant has 5 holes. So, the number of holes will increase in this case and the semiconductor will turn in a P-type semiconductor. And when we make a N-type semiconductor, we add a donor with 5 electrons in the outermost shell, and thus the number of electron increases and it becomes a N-type semiconductor. So, let us discuss about N-type semiconductor. A N-type semiconductor is created by introducing impurity elements that have 5 valence electron, that is pentavalent. Such atoms are arsenic and phosphorus. The diffused impurity with 5 valence electron is called donor atom. So, here we can see a n-type semiconductor. In this n-type semiconductor, there is silicon atomic structure with the impurity doping of antimony, which is represented as Sb. So, antimony have 5 valence electron in its outermost orbit. So, the 4 electron forms the pair with the silicon and a extra electron is left behind. So, overall the conductivity increases due to this extra electron, and the material turns out to be a n-type because of the presence of this free electron. So, let us discuss about the energy band of n-type semiconductor. An impurity of column 5 of the periodic table is introduced at energy level very near to the conduction band of germanium and silicon. Such an impurity level is called donor level. So, let us take an example. In case of germanium, the distance of new discrete allowable energy level is 0.01 electron volt below the conduction band as shown in the figure. Similarly, for silicon, it is 0.05 electron volt. Therefore, at room temperature, almost all the fifth electron of the donor material are raised into the conduction band. Here in this figure, we can see there is a conduction band and a valence band, and a dotted line there represents the Fermi energy level. This Fermi energy level will be discussed in the coming lectures. So, this dotted line forms here is the Fermi energy level, and it is generally at the center in the case of intrinsic semiconductor. But this silicon atom is doped with a n-type material. What is the n-type material? The material which have 5 electrons in the outermost orbit. So, there is one extra electron added in the structure. So, because of this extra electron, the donor energy level or the Fermi energy level will rise up, and it will go just below the conduction band. And now, the transition of electron at room temperature due to this fifth electron is done very easily. There is one point that could be noted. The n-type material as a whole is electrically neutral, since ideally the number of positive charge protons in the nuclei is still equal to the number of free electron and orbiting negatively charged electron in the structure. Let us understand this once again. Although we have doped antimony here with 5 electrons in the outermost orbit, but this structure of antimony will also have a nucleus, and in a nucleus there are equal number of positive ions or protons present. So, that will balance. So, there will be also 5 protons in the nucleus. So, there are 5 electrons and 5 protons. So, they are balancing out each other. So, in a open loop condition, when the loop is not closed, in a open loop condition, this material, this n-type material will be electrically neutral, as there are equal number of positive charge and negative charge. So, moving forward towards p-type semiconductor, the p-type semiconductor is formed by doping a pure germanium or a pure silicon crystal with impurity atom having 3 valence electron, that is trivalent in nature. The elements most frequently used for this purpose are boron, gallium and indium. The diffused impurity with 3 valence electron are called acceptor atom. So, let us take an example of a p-type semiconductor. This figure shows silicon crystal structure with boron impurity. So, here we can see that there is a silicon structure and a boron is added to this structure. Now, what happens here? The boron has 3 electron in the outermost shell. So, this 3 electron will form the covalent bond with 3 silicon atom, and the fourth one will be left out. There will be a vacancy. So, that electron will not be shared between the boron and silicon. Hence, there will be a vacant hole position there, and the structure turn out to be a p-type material. So, this is the energy band structure for a p-type semiconductor. Here we can see there is a conduction band and a valence band at the bottom level, and the figure shows the energy band diagram of the p-type semiconductor. So, in case of silicon and germanium, the atoms from column 3, that is boron, aluminum, gallium, indium, are added impurity levels close to the valence band. So, at 0 Kelvin, these levels are electron free. In this figure, we can see that the Fermi energy level is shifted downwards towards the valence band. At low temperatures, enough thermal energy is available to excite electron from the valence band into the impurity level, leaving behind hole in the valence band. Since this type of impurity level accepts electron from the valence band, it is called acceptor level. Standard doping levels are shown here. So, for the case when we have to have a moderate doping, it is in 10 to the power of 6 to 10 to the power of 8, P or N type. That means one impurity atom in 10 to the power of 6 to 10 to the power of atom, or the ratio of the impurity atom is 1 is to 10 to the power of 6. When we have a lightly doped atom, the impurity level is in the ratio of 1 is to 10 to the power of 11. So, it will have one impurity atom out of 10 to the power of 11 atoms. When we have to have a high doping, we also call it heavily doped materials. Here there is one impurity atom for every 10 to the power of 3 atoms. So, this is represented by P plus or N plus. It means that one impurity atom is added for 10 to the power of 3 atoms. So, when we have a moderate doping condition, we represent it as P or N. When we have a lightly doped condition, we represent it as P minus or N minus, and when we have highly doped condition, we represent it as P plus or N plus. So, in this lecture, we have discussed about the intrinsic and extrinsic semiconductors. So, we have discussed about semiconductor materials. intrinsic semiconductor, covalent bonds between the silicon atoms, charge carriers in intrinsic semiconductor, the effect of temperature on conductivity of semiconductors, extrinsic semiconductors, and energy band diagram of n-type and p-type semiconductors. So, in the next lecture, we will proceed more about the semiconductor devices, and I thank you all for your patience hearing.